Now that the cell has these phosphates attached onto this 3-carbon molecule, it can extract these phosphates, it can harvest these phosphates, and it can transfer them onto ADP molecules to recharge them into ATP. We technically don't call this 3-carbon molecule G3P anymore because it has a different molecular formula. It's had a phosphate added. It's had some hydrogen removed. So different molecular formula, different molecule. We now call this PGA. We're going to see PGA again when we talk about photosynthesis, so that's why I want to bring it up now. But this molecule on the left, the 3-carbon molecule on the left, is called PGA. PGA is going to go into the active site of an enzyme. And this enzyme's job is to rip these phosphates off and transfer them onto ADP. So these are my substrates, ADP and PGA. Now remember, one of those phosphates was an inorganic phosphate. It did not come directly from ATP. That's why I'm drawing that one as pink. Okay, so this enzyme, this is called substrate level phosphorylation. Substrate level phosphorylation. And its name tells you what's going on here. These are substrates. They're going into an active site. The active site is going to rip a phosphate off of one organic molecule and transfer it over to another. So this enzyme is going to rip this phosphate off PGA and transfer it over to another organic molecule called ADP. This is now ATP. So this ADP has been recharged back into ATP, and it can leave. Another enzyme is going to take this PGA with its one remaining phosphate, and it's going to rip that phosphate off and transfer it to ADP. So again, we're just recharging. It's like recharging the battery. We're taking these depleted ADPs, we're ripping the phosphate off of PGA and transferring that over to ADP to recharge this into ATP. The fact that the original source of phosphate was inorganic, that's why I drew it as pink, doesn't change anything about ATP. Like, this is still ATP. I just want to make sure that we understand that originally it was inorganic, just so that you can keep it in your head that, okay, the cell didn't actually spend 4 ATP to get here. It only spent 2 ATP, and then the other 2 phosphates came from an inorganic source, but the cell can use all 4 of those phosphates to make 4 ATP. So what do we get out of this? This is the end. This is the end of glycolysis. What do we get out of all this? Or what does the cell get out of all this? Well, the cell gets 4 ATP. But remember, it had to spend 2 ATP in order to get here. So in reality, the net gain is 2 ATP. What else does it get? It gets these 3-carbon molecules that are left over, right? The phosphates have been harvested. These 3-carbon molecules are left over. We call these 3-carbon molecules, they're no longer called PGA. They've had their phosphates removed. Some enzymes have moved some atoms around, so created some isomers. Some water has been removed. I've skipped a lot of steps because they're not really relevant for understanding glycolysis, but just know that these are now called pyruvate. And then importantly, don't forget, we also have some NADH. We also have some NADH created due to the oxidation of G3P. We have 2 NADHs created. 2 NADHs. So this, in purple, is your net gain of glycolysis. 2 ATP, 2 pyruvate molecules, and 2 high-energy electron buckets, high-energy electron carriers. Now notice, oxygen never came into the picture, right? We talk about how breaking down glucose requires the consumption of oxygen. And that's true, but we haven't gotten there yet. This is an anaerobic process. You do not need oxygen in order to perform glycolysis, which is great. The downside is that glycolysis only produces a very small amount of ATP. Your cells cannot survive strictly off of glycolysis. There are points in time where your cells rely exclusively on glycolysis. If there's no oxygen available, we call this fermentation, and we'll get to this later, but fermentation will only take you so far. If you deprive your cells of oxygen, they will not be able to synthesize sufficient amounts of ATP in order to stay alive. There's still a lot of energy stored in pyruvate, and if cells have a way of further oxidizing pyruvate, they can extract that energy and use that energy to generate significantly more ATP than what glycolysis can produce. We call this process of extracting energy from pyruvate using oxygen, we call that cellular respiration. And that's what we'll get into next.